Okay, so just to get started off with it, we had been talking about the asset path equation, and we had defined the probability of default as the probability of the asset path or the asset of a borrower to fall below the debt obligation. So the asset of the borrower to fall below the debt obligation or the DI. Right? So there is a probability of AI being less than TI. So this is precisely what we want to identify. So this is what the probability of default is all about. So this is what is the probability of default. Now, as we talk about the probability of default, right? And what we are trying to do over here is we are trying to find out an expression. We are trying to find out the factors which will help us assess the probability of default. So the factors should tell us that okay, so and so factors are there which explain the probability of default positively. So which have a positive association with the probability of default. There are so and so factors the which negatively impact the probability of default. So these are some of the areas that we need to work on to understand that yes, this is how the thing is going to be. So this is how the probability of default is affected by the asset path. This is how probability of default is affected by the initial asset price. This is how the probability of default is going to be affected by the Brownian motion and so on. So these are some of the topics that we will be talking about over here. And to define this probability of default, right, one thing that we had identified in the last class was that it is the value of the Wiener variable which creates an impact on the probability of default measure. So given that the probability of default, the Wiener value is less than some value, the asset path would be below the volatility would be below the debt obligation path, and given that it is above a certain value, the asset path would be above the debt obligation line, and hence the probability to default would be much lower. So this is what the overall idea is, right? Now let us just have a look into the following. So what are the things that we had seen? So we saw that the log AT path, the log of AT was driven by the initial value of the asset. It was driven by the average growth rate of the asset, right? And it was negatively impacted by the variation or the volatility. Plus, there was a factor, and so the decisive factor in this entire story is the Wiener process or this Brownian component, because it is this Brownian component which will cause my what should I say, which will cause this particular behavior to increase or decrease, right? So if there is a sudden fall in the Brownian motion, what will happen is that the asset path would go below the debt line, right? On the other hand, so this is what the volatility part is all about. So higher the volatility, lower are the chances of the asset value to be above the debt line. So higher the volatility of the asset, higher are the chances of the asset price to fall below the debt obligation, and hence the challenge arises. So over here, our objective was to study this particular behavior, right? So we had taken up all these three cases, and we had analyzed the impact of volatility. We had analyzed the impact of the intercept, that is the initial asset value, and we had assessed the impact of the average increase in the asset value over time, right? And we have seen that each of these factors are very consistent in the signs and the expression that we have obtained. And one thing that came up very shocking to us, or one thing which came out very interesting over here, is that it was the Wiener process which finally had play the game. So if the Wiener process or the Brownian motion value was above a certain level, then it had pulled up the value of the asset price to such an extent that it was above the price line, above the deadline. On the other hand, if it was below a certain set of values, below a certain cut-off value, then the asset price would be below that, would go below the deadline. So when we tried estimating the probability of default, right, this condition that AI is less than DI, that is where we saw that the imposition that was done on the WBT value, right? And we said that this is the phi ci. So the probability of default that we had created over here was a function of this ci. And this is where we start our today's discussion from. So from the from the Ito's lemma expression, what we got to see from there was that the probability of default was a function of Ci. From Ito's lemma and the BSM asset price path, what we got to see was and as from Ito's lemma and BSM asset price path, what we saw was that the probability of default I is phi Ci, where Ci is the following factor. So one part is di minus log a0 of the ith borrower, right? Minus mu a minus half sigma square a plus sigma a into w, right? So this is what the probability of default equation is all about. Right? Now, when n is a cumulative normal distribution function, or I mean this phi that I'm talking about over here, this phi is a cumulative normal distribution. Phi is a cumulative normal distribution. So the question that we try to ask over here is that so one quick question is Then how does a cumulative normal distribution look like? So we'll quickly refresh the concept on normal distribution and cumulative normal distribution, and from there we'll see how this distribution would look like, and then we'll carry on. So over here it is nothing but a cumulative normal distribution. So what I'm saying is that the CI value that we have is more or less normally distributed, so that the values are more or less symmetric in nature, right? So if there are no sudden shocks or something like that, this distribution of the WA values are more or less similar, because WA itself comes from a normal distribution, right? So the WAT, the Wiener process of the Brownian motion that we did defined over there, had a mean 0 and a variance T, right? So over here, the this distribution phi ci, the values below which WA less than a given set of values, so that will also be a normal distribution. So let us just have a look into this cumulative normal distribution. So what is this cumulative normal distribution over here? So let's very quickly plot the normal distribution once. So over here what we have is the x, or the dependent variable, and over here what we have is the probability of x, right? And what we'll do over here is we'll just plot this distribution. So this is a very symmetric distribution, and this symmetric distribution is known as the normal distribution. So what are the implications of a normal distribution? So basically, a normal distribution is one where which is more or less symmetrically distributed over the values, and given that it is symmetrically distributed over all the values, uh, so symmetric distribution clearly forecloses the uses of or the existence of any, you know, outliers or any such value which can create a skewness in the given distribution. There is a normal distribution that we have over here, right? So this normal distribution is a symmetric distribution, that is, there are no outliers or there are no skewness involved in the data, and the values over here with distributed are more or less very homogeneous in nature. And one very important characteristic of the normal distribution is that it is mean equals to median equals to mode. The mean equals to the median equals to the mode. And this is the characteristic of asymmetric distribution. So that what it says is the percentage of values. So if these are the values, right? So the values lying at this for this end of this tail, and the percentage of values lying to the lower tail are more or less similar in nature, and that mostly the mediocre values and the median values are have the highest chances of being represented as the central value. So tail end values do not appear as representative values in these cases, and hence the challenges associated with skewed distributions are not involved in over here. So this is precisely what the overview is. Now the next question that comes out over here is that how would the cumulative distribution function for uh, normal distribution look like? So what exactly is the cumulative distribution function? So cumulative distribution function is obtained by adding up the probabilities of between different intervals. And this is a cumulative function, it keeps on increasing and then it flattens out, right? So it does not, it's not a case where the function comes down, because since it's cumulative and you are keeping on adding things up to it, what you get is very smoothly increasing kind of a function. So cumulative distribution function for this would look something like this. So in the initial tails, right? So in the lower tails of the value will be very less. Because the middle values it increases something like this, and then it again flattens out. This is somehow a cumulative distribution function looks like. So what exactly is a cumulative distribution function? The cumulative distribution function is a probability. So over here, I'll quickly again refresh the concept of a cumulative distribution function, and then I'll move on. Distribution function. Okay. So over here, what we are trying to do is, so let's just see how a cumulative distribution function would work. Say, for example, I have a probability like this. I tell you that okay, the probability. So the probability of x over here is say 1/3 for all values of x between 0 and 1, less than 1. Right. It is 1/3 for x greater than equal to 1, less than 2. This is equal to 1 by 3 for x greater than. Now what I want to know is that what is the probability of getting a value what is the probability of getting an x less than equal to? What is the probability of getting an x less than equal to 2? So now over here, so if I'm looking to think about a value variable, what is the probability of getting a value with x less than less than? So it means what? So what is the probability of getting x less than equal to 1 plus what is the probability of getting x greater than 1 and less than equal to 2? So less than, right? So over here what will I see is what is the probability of getting x less than equal to 1? It is 1/3, right? 1/3. And between greater than 1 and less than 2 is also 1/3. So therefore the total probability of getting a value x less than 2 is 2/3. So this is called a cumulative probability, where you are adding up probability of two or more sets of outcomes to get two or more different cases to get a single probability value. So when I want, probability x less than 2, then I know that it is less than equal to 1, and then it's greater than 1 and less than 2. So this is what we call cumulative probability, right? So this is known as, or so basically when we are doing it over continuous variables, also when the values are changing continuously, we are continuously keep on adding them up, then the distribution that we get is known as a cumulative distribution function. So it gives me a chance to say or to check. So what does this show? It shows what is the probability that the asset is less than equal to a given level of debt, right? So therefore, this is nothing but a cumulative probability. So when I'm trying to assess that okay, x takes a value less than equal to something, then what I'm doing is I'm adding a multiple probability scenarios and I'm getting to that value. Therefore, this is known as a cumulative distribution function. So this phi dot is a cumulative normal distribution function because this Wiener process WAT follows a normal distribution with the mean 0 and variance a comma and a variance t, right? So, guys, before I go on, just give me 5 minutes time. I'll just be back. So, is this idea of a cumulative distribution function clear to us? Great.